For this lesson, we're going to be looking at limits and their continuity. So the difference between a continuous function and a discontinuous function. So if we look at the graph on the right here, a continuous function, if we said that this was y equals f of x, a function f of x is continuous at a value of x equals a. So on the x-axis, if I'm looking at where the a value is, if the following three conditions are satisfied. So it has to be all three conditions in order for it to be continuous. So the first is that the y value, f of a, is defined. That is, a is in the domain of f of x. So if I'm looking at the a value, is there a solid line? Is there a solid dot at that a value for my y value? So for example, it's not an open hole. Let's write this down here. So for example, for number one, that there is a point, meaning a solid line, a solid point. There's not an open hole. There's not a jump or displacement there. So for number two, the limit as x approaches a, so we're talking about from the left side and the right side, because it just says a, right? That the limit exists. So again, if I'm approaching from the left side and the right side and I get different answers for the limit, then the limit does not exist. So for example, for this graph, if I'm approaching a from the left-hand side, right, I'm nearing a y value of here, y at a. If I'm approaching the function from the right-hand side, approaching a, my y value is the same value. We don't know exactly what the value is here, but it's the same value. So the limit exists. And for the third and final one, the limit as x approaches a of the function is equal to when I look at f of a. So what I mean there is the limit as x approaches a, so part of number two here, if I'm looking at the limit from either side that it exists and I have the same y value, that would be equal to and the same as if I actually looked at exactly a. F at a, not a limit, but right, f at a is equal to what y value at exactly that, that value of a, or that numerical value. If there was a number given there, I would have a number answer here. Is that equal to the limit? So let's write that down. So what I mean by f of a is at exactly a. Is the same as the limit. That answer is the same as my limit answer. And if all three of those things hold true, then it would be a continuous function. Also looking at the graph, you can see that this line is continuously, right? Is continuous from left to right, which is how you'd read the graph. There's no breaks, again, there's no open holes. But for example, just to show you, if this pretend was an open hole and I had my solid dot on top, then my limit as x approaches a, my limit as I approach from the left, my limit as I approach from the right, I'm nearing the same y value, but f at a, the y value here, at a would be not where the open dot is, but where the solid dot is, and I would have two different y values and they would not equal each other. So just as an example, in this case, number three would not be satisfied here. If it was that example, then that would not be a continuous function. Okay, so let's move on to more examples of discontinuous functions. So a function with an open hole, like we were just talking about, right here would be removable discontinuity. So it's like I'm taking part of the graph here and removing it and putting it on top because there's like an open hole there, a space, and it's moved either up or below. would be removable discontinuity. We have what's called a gap or jump discontinuity, we'll call it from now on. So the function is continuing here, and then we have a space and a jump, and then it continues on. Or we have infinite discontinuity, which means infinitely, right? These lines will never touch each other. And we have an asymptote here along the A value. So along the A value, I don't have a value, right, for Y in the positive direction. I don't have a value for Y in the negative direction because none of the graph is coming in contact with A. So that's infinitely and plus if you look at the two parts of the graph, it's discontinuous, right? This line is not continuing. It stops and there's a break, and then it continues on this way. Same here, it stops and there's a break, and then it continues on. So a function f of x is discontinuous at a value, x equals a, if any one of the conditions are not satisfied, right? So this is just the same as what was written above. If a is not in the domain of f of x, then we would not have a continuous function. If the limit as I approach a from the left and the right hand side are different values and the limit does not exist, then it would be discontinuous. Or if again, the limit as I approach a is a different value than exactly at f of a, exactly at that value of x, do I get the same value of y as I would for the y value of the limit? So let's look at these up above and see which one of these three cases, because if we're already saying that these are discontinuous graphs, which one of the three is it failing, for example? So for the first one here, f of a is defined. We're looking at removable discontinuity here. That is, a is in the domain of f of x. So there is a point, there's no open hole, etc. So as I'm approaching here, I would have a y value. As I'm approaching here, I would have a y value. The limit as x approaches a, right, exists. I would have the same y value. But here for number 3, as I'm approaching, if I move this up a little bit here, the limit as I'm approaching a would be this y value here, but f at exactly a would be this y value above. So they have different y values. So in this case, it would be the third case, number 3. Oh, number 3 is not satisfied, which is what makes it discontinuous. What about number 2, the jump that I have here? F of a is defined. I have a value of a that's defined. There's a solid dot here, right? So I do have a value that would be in the domain. Same with this a, right? There was a solid dot, so I do have a value that's in the domain. Now let's approach from the left and let's approach from the right to see if the limit exists. If I'm approaching from the left, I'm nearing this y value. If I'm approaching the function from the right, I'm nearing this y value. So again, my y values would be different here. So my limit does not exist. So in this case, it's number 2. If one of them fails, I wouldn't even bother looking at the third, for example, right? Because you only need one of the conditions to not be true for it to be discontinuous. So in this case, it's number 2 that's not being satisfied. And looking here at number 1, at the third example, the limit as x approaches a, right, from the left and the right hand side, does that exist? But first, let's just look at the first example, the first statement here. F of a is defined. That is, a is in the domain of f of x. So if I have a value for a? So I have no y value here for a, right? Like here, my a value is whatever this y value is. I have a solid line, a solid dot. Here I have an a value. Here I do not have an a value. So it's failing right away on the first statement. So number 1 is not being satisfied here. And this is again an asymptote from last year. I don't know what I was writing there. Okay. So if the graphs, to continue on, are not visible to you, if the graphs are not there, then we're going to have to figure out a way looking at equations to determine continuity. So looking at a graph, there's the three rules that we will look at to decide if a graph is continuous, like the one above, or discontinuous, like these three below. But what about if we're looking algebraically? So to evaluate a limit algebraically, substitute the value that is approaching x into the equation. If the value exists, so I get a numerical value, whatever answer, 4, -6, 1000, then I have evaluated the limit and the limit exists. So there can be continuous parts of a discontinuous function, right? So if we look at this first graph on the previous page, this is discontinuous here, but let's just say I was looking at, just to have an example, over here, let's say is -1, a value of -1 on x. To the left, to the right, it's solid. That would be a continuous part of the graph, but there's a portion that's discontinuous. So if I were to sub in a value at that moment in time, at that value, it would be continuous by substituting the value that is approaching x. Then I've evaluated the limit. This means that the function was continuous, but again, only at that x value is what we're saying. If I plug in the x value and I have an indeterminate, which means I actually get an answer of 0 divided by 0. I get 0 as the numerator and in the denominator. Then it's basically giving me a little hint, a little prompt there that, you know what, this can work out, but I need to do more work. So then I have to factor or rationalize, expand, simplify the equation before I substitute the x value in again. So the result does exist and the limit has been evaluated. And this means that the function would look like removable discontinuity at that x value. So again, removable discontinuity would look like this. So I do have a function that's existing, but at that x value, I have a discontinuity, which is what it's alerting us to if I receive a 0 divided by 0. And I'll explain, we should know how to do everything here except for the rationalizing, and I'll explain how to rationalize when we get to that example. If the value results in an undefined value, so a number divided by 0, so it can be, so this number on top here is not 0. So for example, it doesn't matter. 4 divided by 0 can be -7 divided by 0, but a number divided by 0, then the limit does not exist. So this means that the function has an infinite discontinuity at that particular x value, means I have an asymptote, right? Infinite discontinuity would look like this one here. At that x value, there's a discontinuity. I have no portion of the graph going through that x value, going through that a value. So that would be the jump discontinuity. Just moving this up, sorry, so you can see that. And it would look like a piecewise. For jump discontinuity, which we haven't done, we've looked at an example now of removable discontinuity algebraically infinite discontinuity. If there's a graph that's representing jump discontinuity, then it would look like a piecewise function, which let me get rid of this here, which is further ahead in the lesson. It'll be in the second video. You can see here we go, piecewise function. So we'll go over that as our last example. So that one we will approach. It's just not written here yet. So let's do some examples here. evaluate each limit if the limit exists. So we're going to evaluate the limit of, as x approaches -3 of x squared. So what I want to do is replace the x with the -3. I don't have to write the limit anymore, or I don't have to write that x is approaching anymore because we're evaluating it at that exact value now. So we're evaluating it like at f at -3 for the function of this parabola y equals x squared, right? So also, if we think about it, if we know that this is y equals x squared, we know this is a parabola. We know a parabola is continuous, right? There's no jumps. Just to write that down, there's no breaks. There's no jumps. There's no open holes. So it should be a continuous function. I should get a numerical value. So if I plug in, instead of x, I'm plugging in -3 squared. I have a value of 9, right? So 9 would be, this means the very first example here, just to go back up. 9 would be the first bullet here. The value exists. I've evaluated the limit and it's continuous at that x value is all we know of right now. So it is continuous. So let's look at this next example. The limit as x approaches 2, right, from both sides of 7. So the equation would be y equals 7. So let's go back and think about this. I knew y equals x squared was a parabola. What's y equals 7? Do you remember what that looks like if I was to graph it? 1, 2, 3, 4, 5, 6, 7 would be a horizontal line, right? At y equals 7, I have a horizontal line. So is there any breaks? Does it look discontinuous? Is there any holes or jumps or anything? It looks pretty continuous to me. So I should get an answer. And if I were to look, I'm approaching 2. So just to change the color here, at x equals 2, right here, what is the y value? And the y value would be 7. So my answer for this would be just 7. I don't have anything to plug in. I don't have an x variable to plug 2 into, but I know that an x value of 2 would be 7. Any x value here, my answer, my y value would be 7 for any of the x values. So this would be a continuous function, right? So this expression here, x cubed plus 3x minus 6 is a polynomial function. So we know a polynomial function should be continuous, just to kind of get an idea ahead of time. We should expect a limiting value that exists, but all we need to do is when I see x, I sub in the value of 5. Put it in brackets. So 5 cubed plus 3 times 5 minus 6. 5 times 5 times 5 again is 125 plus 15 minus 6. So 140 minus 6 is 134. So it exists. It's continuous. Okay, what about D, E, and F? I'm going to need more space. Let's move this up. What if I have the limit as x is approaching -1 with the square root of 2x plus 5? So again, just plug in the value of -1 underneath the square root sign, 2 times -1, and see what we have. So that equals the square root of -2 plus 5, which would equal the square root of 3. So the square root of 3 is a number, so it's continuous. We do get a decimal. We can write it as a decimal, but we know that it's already a number. We know it's not a number over 0 or 0 over 0, so we know it exists, and we can just leave it written with the radical symbol there as the square root of 3. So if we were to look at a function like this, just to give you a brief idea, right? It looks something like this, square root of 3. So we can see that that looks continuous. Here I'm looking at the same thing. 2x plus 5 square rooted, but I'm looking at the limit as x is approaching -4. So if I sub in -4 for x this time, I have -8 plus 5 is now the square root of -3 and not +3. So I can't have a negative root, right? I can't square root a negative, so this answer is undefined. So then it's not continuous. And if we look at what's happening here, this would be the same graph, right? I'm using the same equation expression, but -4 would really be, let's just change my color here. Let's say out here. So there is no value, right? If I'm looking at the limit as x is approaching -4 from either side, I don't have a y value. My y value would be undefined. So that's why we're getting that answer there where it's not continuous at that moment. Let's look at a different example here. The limit as x is approaching 0 for x minus 3 multiplied by 5x squared plus 2, which is also, right, if I took x and multiplied it by 5x squared, I'd get 5x cubed. So it's a cubic polynomial. So we should get that the value does exist, that it's continuous. Let's check it out by plugging in 0 for x. 5 times 0 squared plus 2. 0 take away 3 is -3. Multiplied by 0 squared times 5 is just 0 plus 2. 0 plus 2 is 2, and I get a value of -6. And right, it doesn't matter if it's negative or positive. It's just the fact that it's not 0 over 0 or a number divided by 0. So it can be positive or negative. So the limiting value does exist, and it is continuous as I'm approaching 0.